Modern higher education faces a specific mandate, transitioning students from passive recipients of knowledge to active, lifelong, self-directed learners. Self-directed learning relies on three intersecting pillars identified by theorists Knowles and Candy: metacognition, motivation, and behavior. In a 2026 quasi-experimental study by Ditsiri and colleagues, researchers tracking first-year undergraduates documented a rapid, statistically significant spike in these exact skills. This table details the pre- and post-test data. The students' self-directed learning scores jumped from an average of 22.80 to 26.50. With a p-value of 0.00, this indicates a significant behavioral shift. The intervention responsible for this shift involved no changes to the core curriculum. Instead, the researchers deployed a purpose-built, proactive virtual reality platform. Analyzing these results requires evaluating the platform's specific design as an engineered cognitive scaffolding tool. New undergraduates often encounter a severe logistical obstacle. Navigating a geographically dispersed university campus across multiple centers creates immediate spatial anxiety. This spatial uncertainty exacts a psychological toll. The constant effort required just to locate classrooms and resources drains cognitive bandwidth and induces passivity. When students are overwhelmed by basic logistical survival, they lack the mental resources required to engage in metacognitive planning or to learn autonomously. The researchers posited that bypassing physical reality entirely through a low-risk digital environment could remove these constraints and free up mental capacity. The data suggests that reducing spatial friction is a critical prerequisite for building learner autonomy. This conceptual framework maps the digital intervention to pedagogical outcomes. On the left, the proactive digital platform relies on three architectural features. Immersion isolates the student via 360-degree environments. Interactivity demands active decision-making, and presence engineers telepresence, creating the sensation of being physically present. Combining these three features facilitates a state of self-regulation and spatial problem-solving by removing the risks of real-world failure. Before analyzing student outcomes, the researchers mathematically validated the digital tool's instructional design. They utilized expert evaluators to stress test the platform's system stability, responsiveness, and environmental realism. This table shows the expert evaluation results. The overall quality rating was 4.67 out of 5, with audiovisual clarity receiving a flawless 5.00 score. Next, they applied E1, E2 efficiency criteria. E1 measures process efficiency during active learning tasks, while E2 measures product efficiency based on final outcomes. Looking at this data, the platform scored an 80.33 for process and an 85.17 for product, surpassing the established 80-80 baseline for instructional media. These specific empirical validations separate a pedagogically sound tool from a superficial technological novelty. With the system architecture validated, we can examine the behavioral response from 120 first-year students. Post-intervention satisfaction data reveals which psychological triggers the virtual reality platform activated. This table breaks down user feedback. The highest-rated behavioral impact was the platform's ability to enable students to engage in learning independently. Right below that, the data shows the platform motivated students to explore and pursue further learning on their own. The psychological mechanism here is straightforward. When spatial exploration carries zero physical risk, the fear of failure is mitigated. This engineered psychological safety serves as a catalyst for the transition into self-directed, autonomous behavior. Returning to the full conceptual framework, the data supports the hypothesis. Purposeful virtual reality design directly generates self-directed learning skills. Based on these findings, institutions can implement three actionable directives. First, deploy virtual reality as a proactive orientation tool to reduce logistical friction before classes begin. Second, integrate virtual reality exploration within a flipped classroom model to encourage autonomous engagement outside of standard lecture hours. Third, establish permanent virtual reality stations in centralized campus hubs to facilitate on-demand, self-initiated learning. By adopting proactive digital scaffolding, higher education institutions transition from static transmitters of knowledge into active facilitators of lifelong learner autonomy.